Touch a metal doorknob and a wooden table in the same room. Why does one feel cold if they're literally the same temperature? If you've never actually tried this on purpose, do it the next time you can. Same room, same air. Give both objects time to sit there for hours. Then put one hand on the wood, one on the metal, and just notice your immediate stubborn impression. The metal feels colder, not a little colder. Colder in a way your brain treats as obvious truth. So here's the first uncomfortable fact. Your sense of hot and cold is not a thermometer. It's a detector for something else. And if school left you with the feeling that temperature is basically how hot something is, or even that it's how fast the molecules move, that's not wrong in every situation, but it's not what temperature actually means. Because temperature is one of those ideas in physics where you can't get the meaning from a slogan. You only get the meaning by asking, what do we do when we measure it? What changes when we put things together? And what stops changing when equilibrium is reached? Let's start with that doorknob. When you touch the metal, energy leaves your skin quickly. The metal is good at carrying energy away from the spot you touch, so the tiny patch of metal under your fingers stays ready to absorb more. Your skin cools fast, and your nerves interpret that rapid cooling as cold. When you touch the wood, energy leaves your skin slowly. Wood is a poor conductor. The spot under your fingers warms up and just stays warm. The flow slows down, and your nerves interpret the smaller heat flow as not cold. But notice what we just said. We didn't say the metal is colder in temperature. We said it pulls energy from you faster. Your nerves respond to the rate of energy transfer, how quickly your skin is changing, not to a number sitting inside the object like a hidden label. That is why a metal bench feels freezing on a cool day and blistering on a hot day, not because it has special temperatures, because it is excellent at exchanging energy with you. If you want a simple experiment that makes this impossible to ignore, try this. Put a metal spoon and a wooden spoon in the same cup of room temperature water for a while, then touch the handles. If your senses were measuring temperature, they'd tell you the same thing. They won't. They'll tell you the metal is cooler. And this is the first step in the school never taught you part of the title. Temperature is not a sensation. Sensation is about change. Temperature is about something else. So what is temperature really? A lot of people learn the sentence, temperature is the average kinetic energy of molecules. It sounds good. It's got molecules. It's got energy. It's got the word average, which feels statistical and grown up. And in one very important case, an ideal gas, it works beautifully. In that case, the temperature really is proportional to the average kinetic energy of the molecule's random motion. But if you treat that sentence as the definition of temperature, you immediately run into trouble the moment you step outside the ideal gas world. What about a solid where atoms vibrate in place rather than flying freely? What about a liquid where motion includes rotations and vibrations and interactions and not just flying around? What about a system where the important energy isn't motion at all, but an internal energy level? What about light, radiation, where there are no molecules at all? So the slogan is useful, but it can't be the foundation. You don't build a definition on something that stops applying to half the universe. Here's a more honest approach. Let's do what Feynman loved to do. Forget the word for a moment and look at the behavior. You have two objects. You put them in contact. Something happens. Energy moves between them. And after some time, something stops happening. There's no longer a net flow of energy in one direction. Things settle. That settled state is the key. The most basic meaning of temperature is tied to what changes and what stops changing when things are allowed to interact. Suppose you have a cup of hot coffee on a table. You put a colder spoon into it. The spoon warms up. The coffee cools down slightly. Energy flows from coffee to spoon. This continues until the spoon and the coffee stop changing, until they come to a stable condition. Now imagine you do this with all sorts of things, different materials, different shapes, different sizes. The details differ, but one big fact repeats. There is a certain condition where when two systems are in contact, they no longer have a net tendency to exchange energy as heat. That condition is what we call thermal equilibrium, and temperature is the number that labels thermal equilibrium. That sounds abstract, so let's make it concrete. A thermometer is not a magical temperature reader. It is a little physical system that you allow to interact with the thing you care about. It changes, maybe it expands, maybe its electrical resistance. It shifts, maybe its voltage changes, until it stops changing. When it stops changing, it has reached equilibrium with whatever it's measuring. So a thermometer is basically an object you're willing to sacrifice. You let it be altered by contact until it reaches a stable state, and then you take that stable state and map it to a number. That's the measurement. Notice what's hiding in this story. We are assuming something subtle, that it even makes sense to talk about the same temperature across different materials and different thermometers. Why should that be possible? This is where one of the quietest laws in physics comes in, the one many people never hear the name of, but which makes the whole idea of temperature possible. If system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. That's it. That's the statement. It sounds almost too boring to be a law, but it's the reason thermometers work, because it means there exists a consistent way to classify systems into equilibrium groups. If A matches B and B matches C, then A matches C. That transitive property is what lets you assign a single number that all these systems can share. If that weren't true, you could have weird situations where a thermometer agrees with a cup of water and also agrees with a block of metal, but the water and metal still exchange heat when put together. Then temperature would be a mess. It wouldn't be a single variable. It would depend on which instrument you used. You couldn't build a scale that applies universally. But nature is kind in this way. Thermal equilibrium behaves consistently enough that we can create a temperature scale. So at the deepest practical level, temperature is the property that is equal for systems in thermal equilibrium. If you remember only one sentence from this whole video, that one is more reliable than average kinetic energy. But of course, you don't want just a definition you can memorize. You want the meaning. You want to feel what temperature is doing. So now we ask the next question. What is it about the microscopic motion that makes two systems stop changing when they're together? To get there, imagine a thought experiment. Picture two boxes, each containing a gas. The boxes are separated by a thin wall that allows energy to pass through, but does not allow molecules to cross. One side starts hotter, one starts colder, whatever that means for now. We put them into contact through this wall and wait. What happens microscopically? Molecules are flying around, colliding, they hit the wall. The wall jiggles, vibrates, transmits that vibration. Energy is exchanged through these microscopic collisions. In time, you reach a steady state where energy is still being exchanged in both directions. Molecules on both sides are still colliding with the wall, but there is no net flow from one side to the other. In that state, what must be true? It can't be that molecules on both sides stop moving. They never stop. Even at ordinary temperatures, the microscopic motion is intense. So changing can't mean stopping motion. It must mean something statistical. The rate at which energy transfers from left to right equals the rate from right to left. That's already a clue that temperature is a statistical concept. It's not how fast one molecule moves. It's something about the ensemble, the whole crowd of molecules. Now, in a gas, we can make this more explicit. Take an ideal gas. Molecules that hardly interact except when they collide, like tiny billiard balls. In that case, the pressure is caused by molecules hitting the walls. The faster they move on average, the more momentum they deliver per second, the higher the pressure. And if you compress the gas, you do work on it, increasing the energy of motion. It gets hotter. This is where the connection between temperature and kinetic energy comes from. In that simplified world, temperature is proportional to the average kinetic energy of translational motion. But notice how we got it, not by declaring it, but by connecting macroscopic measurements like pressure to microscopic motion, and then noticing that the equilibrium condition between gases corresponds to matching a particular average energy scale. If you've ever seen the equation average kinetic energy per molecule, E to JOS 3 kB/T, that's the famous bridge. And it's not just a random constant. That Kb, Boltzmann's constant, is the conversion factor that tells you what a Kelvin means in joules per particle. If you want to feel the scale, at room temperature, Kbt is about 4 times 10 to the minus 21 joules per molecule. That's a tiny number in human units, but on the molecular scale, it's huge. It's the typical energy associated with random thermal motion. So one of the most useful meanings of temperature is this. Temperature sets the energy scale of microscopic randomness. When T is higher, the random energy per particle is larger. and more energetic microstates become common. When T is lower, the system is confined to lower energy behavior. This is why temperature shows up everywhere in physics: chemistry, materials, electronics, astrophysics. It's not just how hot, it's literally the knob that controls how much thermal energy is available per degree of freedom. But even this energy scale idea still isn't the final meaning, because you could still interpret it as it's about speed, just with a conversion factor. The deeper meaning is about probability. Here's the key thought. In any system with many microscopic possibilities, thermal equilibrium doesn't pick a single microstate. It picks a distribution over microstates. It's like this. If you shake a box of coins around and let them settle, you don't get a single predetermined pattern every time. You get a random pattern, but you get patterns with certain probabilities. And the more you shake, the more energy you feed in, the more patterns become accessible, and the more evenly probability spreads out. Temperature plays that role in physics, but with energy. At a given temperature, the system doesn't have one energy. It has a range. It fluctuates. And the relative probability of different energies depends on temperature. So the most general meaning of temperature is, it is the parameter that tells you how the probabilities of states depend on energy and thermal equilibrium. That sounds heavy, so let's ground it again. Imagine you have a staircase and you're blindfolded and you keep taking steps up and down randomly. If you're only allowed to spend a tiny bit of energy, you'll mostly stay near the bottom. If you're given a lot of energy, you'll explore higher steps more often. Temperature is like the allowance. It doesn't dictate which step you're on, but it changes how often you end up on higher energy steps. In physics language, this is the difference between saying temperature measures energy and saying temperature controls the distribution of energy. And that distinction is not a philosophical nuance. It's what temperature actually is. Because in thermal equilibrium, systems do not sit at one energy. They fluctuate around a mean. They exchange small packets of energy, and temperature is the number that determines the size and pattern of those fluctuations. Now, if you've heard of Maxwell-Boltzmann distribution, that's one example of this idea for speeds in a gas. It says, at a given temperature, molecules have a range of speeds. Most have moderate speeds, fewer have very high speeds, and the shape of that distribution depends on T. That's why average kinetic energy is not enough, because the distribution matters, not just the average. Two distributions can have the same average but different shapes, and they won't behave the same way when they interact. The fact that equilibrium leads to a particular distribution shape is what temperature is encoding. So what does it mean that two objects have the same temperature? It means if you let them exchange energy freely, there is no net energy flow because their microscopic energy exchange rates balance. Statistically, they're tuned to the same distribution rules. They're playing with the same probabilistic dice. That's the real meaning. Temperature is not a feeling, not merely an average. It is an equilibrium parameter that sets the statistical spread of energy and the direction of spontaneous energy flow. Now, you might be thinking, okay, that's elegant, but why do we need a whole constant, Boltzmann's constant, in the first place? Why isn't temperature just measured in joules? Excellent question, and this is the moment where modern physics and the history of measurement collide. Historically, temperature scales were built from practical thermometers, expansion of liquids, melting points, boiling points. You create a scale that's easy to reproduce. Then you discover later that there is a deep connection between that scale and microscopic energy. So you end up with a conversion factor between temperature units and energy units. That factor is Boltzmann's constant. But here's the twist. In modern SI, we essentially flip the story. We now treat Boltzmann's constant as fixed. The Kelvin is defined in a way that ties temperature directly to energy at the microscopic level. In other words, the official measurement system has agreed that temperature is so fundamentally an energy scale that we anchor the unit to the energy conversion constant. This is not just metrology trivia. It's the universe telling you what temperature really is, a way of measuring energy per degree of freedom, per particle, in a system of many possibilities. Now let's check our understanding against the original paradox. Why does metal feel colder than wood at the same temperature? Because your body is not measuring temperature. It's measuring heat flow, and heat flow depends on thermal conductivity and heat capacity, and how quickly the object can carry energy away from your skin. The metal creates a bigger energy gradient in your skin faster. Your nerves report cold. But the thermometer, if left long enough, reaches equilibrium with both objects and reports the same temperature, because temperature is about the final equilibrium state, not the transient rate of energy transfer. So school didn't exactly lie to you. It gave you the quick version. Temperature is a measure of hotness, and in a gas it's proportional to average kinetic energy. The problem is what got left out. What got left out is that temperature is not fundamentally about hotness. It is fundamentally about equilibrium and statistics. It is the variable that becomes equal when systems stop having a net tendency to exchange energy as heat. And microscopically, it is the parameter that shapes the probability distribution of energies and motions. Once you see that, the world changes slightly. The radiator in your room isn't full of heat. It's a system with a certain temperature, meaning its microscopic degrees of freedom are distributed in a certain way. When it touches colder air, energy flows because the distributions are mismatched, because the equilibrium parameter differs. The air itself isn't a uniform, quiet thing. It's a storm of molecules colliding billions of times per second with a spread of speeds and energies. Temperature is not one speed. It's the shape of that storm. And the reason we can measure temperature at all is because nature gives us that consistent equilibrium property. The fact that same temperature is a coherent transitive relationship across systems. That is the hidden structure behind every thermometer you've ever seen. If you want one final thought to carry around, temperature is the number that tells you what thermal equilibrium means for a system and how energetic its randomness is. And if that makes you a little dissatisfied because it feels like we replaced a simple word with a deeper one, that's actually a healthy reaction, because physics isn't supposed to make you comfortable with slogans. It's supposed to make you comfortable asking, what do we mean exactly, and what would we measure if we tried? Next time you read the weather and see 25 degrees, try quietly translating it in your head, not into nice day, not into warm, but into this is the microscopic energy scale of the air's randomness, the knob that sets the distribution, and of molecular motions and the value that would equalize if I put this air in contact with something else long enough. Suddenly temperature stops being a vibe. It becomes a piece of the machinery of reality.